Good afternoon, everyone. I am Chandrasekhar. I am leading the engineering core at SEDI. Our company is actually focusing on building autonomous solutions which can maintain high availability for cloud-native applications, while also making sure they're running at the optimal best. So we do that by identifying lower order tasks which are better managed by. Sorry, can you all hear me? Okay. So we actually identify lower order tasks which are actually better managed by machines and which are inherently safe, executing them in an autonomous fashion so that those manual person, the human or SREs who are in charge of executing those tasks, they can actually focus on higher order tasks. So in my company, I focus on the Kubernetes side of solutions for our product. Back in 2006, when AWS launched, it was launched as an IT infrastructure service, which can be accessed over the web, and it can also be managed over the web. So it gave its users enormous capabilities to actually scale up and down the infrastructure without really having to pay upfront for all the infrastructure cost. Fast forward to 2022, we have seen enormous increase in the cloud adoption. We are dealing with more and more managed services with which the users can really focus on building the solutions without really having to worry about the underlying infrastructure. Kubernetes clearly falls into that managed service category. So you can define the resource requirement, you can define how the application works, and let the Kubernetes system manage it for you. So you expect a lot of modern features from the managed services like scaling, automated deployments, and all. Kubernetes has all those features. So one of the questions that we always get is, if Kubernetes is such a capable system, why is there a need to optimize in the first place, either from a cost or a performance standpoint? If you have used Kubernetes in the past, you already know that this is actually not the case. Kubernetes might let you up and running in a very quick pace. But to actually get a fine-tuned Kubernetes cluster and workload requires a lot of effort. The main reason this happens is due to the fact that the Kubernetes is structured. Kubernetes lets user define its requirement, and Kubernetes satisfy it for them. So it has a lot of bells and whistles with which a user can fine-tune the cluster and application to the real needs they are looking for, which is actually one of the reasons why Kubernetes is popular in the first place. But if you see, that also adds a lot of responsibility on the user to make sure that Kubernetes is configured in the best possible way to get the best outcome from Kubernetes. So as I mentioned, we have seen enormous increase in the cloud spend. One of the Gartner reports projects that the cloud spending is going to be north of $480 billion. But there are so many other reports, like the one that I've quoted here from Flexera, which indicates that a lot of those cloud spending is actually not being utilized in the proper way. There is a lot of wastage, around like 35% of it. And the story in Kubernetes is not much different at all. On an average, in Kubernetes, the deployments only utilize 20 to 40% of the requested resources. The rest of it is actually being wasted. So there is clearly a need for optimization even in Kubernetes. So usually, when people start with the optimization, think of it as a balancing act. In fact, it is a balancing act. On the first case, you have to make sure your workloads, your application has enough resources so that it can perform at its expectations. And at the same time, you have to make sure that there are no wasted resources. All the idle resources are cut off, and there is no cost wastage at all. In fact, a lot of companies or a lot of teams actually start thinking about optimization when the cloud cost actually hit a certain limit. So the first priority usually comes from cost optimization. So people usually think about, okay, we are already wasting a lot of money. We are already seeing the wastage. Find out all those over allocations, cut it down, and that's pretty much all you need. But in fact, it is actually way more than that. Different application behaves in a different way. So it is a little bit critical that a deeper analysis of this application is required to really configure it in the right way. There could be a lot of hidden opportunities. In the sense, it may not be apparent evidently that an application might behave in a certain way, and this is basically the requirement for an application to perform the right way. But using some deeper analysis on different conditions, we might be able to unearth that one. So just to explain that situation, we have a web application with a performance requirement of under 10 milliseconds on an average traffic load of 250 requests per second. So we started with the configuration. It was a web application, so we were able to actually horizontally scale it. So we started with the configuration of the individual instance with what we got from developer, based on some standard numbers that applies for web application, and tuned based on the load and performance environment. So our goal was actually to figure out what is the right number of replicas with which we can meet the performance need. So in this case, using 10 replicas and an individual pod configuration of 1 GB of memory and 1 core CPU, we were able to actually get the performance requirements. And the cloud was also within the budget. So which looked totally fine, just experiment on the replicas, and we got the numbers. But in fact, using some deeper analysis and understanding how the application works on different conditions, we were able to identify that this application is actually a little bit more memory intensive. It performs better if you are throwing in more memory. And it is not too critical about the CPU in general. So using some changes, we were able to actually get a better performance with lower number of replicas. In this case, 6 replicas, and slightly adjusted configuration on individual pods. In this case, we had to bump up the memory by a little bit to 1.2 GB. And we were also able to reduce the CPU, and using a different VM, which is actually fine-tuned for memory-intensive applications, we were able to get 6 milliseconds. Initially it was 9, we were able to get 6 milliseconds, and even the cloud cost for that application also went down. So these are the different configurations which may not be apparently visible when you're looking at the application behavior. So for the course of this discussion, we'll keep the high-level goals for optimization as attaining the best performance while making sure the cost is at the minimum. And of course, the main thing is actually to make sure your application is at the highest availability. Of course, there are exceptions to this rule. There could be batch applications where you're not too much concerned about the performance. You could actually take a hit on the performance, which probably may not have a big impact on the business. But there could also be other applications like certain web applications where performance is key. So you might be able to actually take a hit on the cost to actually get the performance that you need. So, but in general, let's keep the high-level goals as maximizing performance while lowering the cost. Optimization is also like multifaceted. You could do it at different levels. You could do it at the code level. You could configure your VM parameters, or maybe specific language level customizations, just to name a few. But again, for this session, we'll keep the optimization to the levers which are available in Kubernetes that can be utilized to actually get the best performance and the cost benefits of applications, pretty much all the applications which are running on Kubernetes. And that includes the HPA, VPA for scaling resources, cluster level auto-scaling, and also the main thing is configuring the resources in the right possible way, specifying the resource requirement on each individual application. Now, the most critical thing is how to configure these knobs. Now that we know the knobs which are available in Kubernetes, we have to actually fine-tune them in the best possible way. To do that, you have to look at the application behavior. And the most common way of doing that is actually looking at the metrics of the application. And the next thing is figuring out the inflection point. How does your application behave? At what level of load can your application take in? So that has to be figured out, either using thresholds or some kind of an inflection point. And the last thing is, at a cluster level, looking at the scheduling requests. You could have heterogeneous applications with different resource requirement. Looking at those different resource requirements, you have to figure out what is the right infrastructure which could meet your resource requirement. Now, looking at the knobs, these are, if you are familiar with Kubernetes, these are pretty much standard things that you always do or use on a day-to-day basis. So auto-scaling, using auto-scaling at a resource level, you can actually increase or decrease your pods to actually meet your application demands, reduce it so that you can reduce the cost. So the knobs which are available for that one is HPA and VPA for the pod auto-scaling. And of course, you want to actually supplement that with some kind of a cluster level autoscaler so that you can complement those changes in the resource requirement at the infrastructure side as well, using some kind of form of a cluster autoscaler. And that's usually done by changing the number of nodes which is backing your cluster. So looking a little bit deep into the HPA and VPA, let's look at HPA. HPA works for mostly stateless kind of an application. They are usually the ideal candidates, but it doesn't mean that they are the only ones. So if your application can actually spawn more instances, and those instances are quickly take up the additional workload, or you can evenly distribute the workload into these nodes, you can probably utilize the horizontal pod autoscaling. Kubernetes also supports autoscaling on stateful applications as well, but it totally depends on the architecture of your application. Say, for example, if your application has a dependency on a very specific persistent volume, and you need write access to it, and that volume can only be shared with write access to only one instance, your application is probably not conducive for horizontal scaling. In such cases, you can always rely on vertical scaling. You are basically throwing in more resources, more CPU, memory, or GPU, if that's the type of application that you're dealing with, so that it can handle more workloads using the same instance. And some of the best practices when you're using HPA or VPA or Kubernetes in general is to make sure you define resource requirements for each individual workloads. So going back to that first case, where you want to actually let Kubernetes do its job at its best. To do that, Kubernetes needs to know what is your priority, what kind of applications you have, the nature of the application, and where should Kubernetes throw in the resources so that it can schedule at the best possible way. Kubernetes has an excellent bin packing algorithm, so to really utilize that one, it is really critical that each individual application has its resource requirements defined. And to really optimize, you want to actually go optimize or right size your application both vertically and horizontally. At this point of time, there are some constraints using HPA and VPA in tandem using the same metric. But I believe this is just going to be a temporary constraint, because we have already seen solutions like multi-dimensional pod scaling, which are already available in beta. So using those techniques, we should be able to actually right size in both directions, both vertically and horizontally. Even if you have those constraints, you probably might have to actually go in and manually configure the other dimension. And of course, when you're using workload scaling, you are actually letting the application scale up and down depending on the demand. That also needs to be complemented with a cluster autoscaler. So let's say your application is demanding more pods. If there is no infrastructure to back it, the scaling just won't work. So it is super critical that there needs to be some kind of an autoscaler backing Kubernetes. And under the hood, if you're looking at EKS, your cluster is backed by worker nodes. And worker nodes are nothing more than EC2 instances. So you need to make sure some kind of a scaler is set up so that you can throw in more EC2 instances or more worker nodes to meet your application demands. And if you are not too much interested in managing your infrastructure at all, EKS actually gives you that option as well. You can always go with Fargate and Kubernetes supplement your infrastructure needs without really you having to configure them. And when you're dealing with cluster level autoscaling, you of course have a choice to actually go with manual scaling. If you're on EKS, you can actually define autoscaling group, manually go and change the desired replicas depending on the workload that you are seeing in Kubernetes. This will probably work if your cluster is pretty much static, the resource requirement of your cluster is pretty much static. Or if you're testing it out, then you can probably start with manual autoscaling. But if you are dealing with most of the production-like scenarios where your resource requirement changes, you need to use some kind of an autoscaler. And if you're on Amazon, you have primarily two main choices. One is the cluster autoscaler. The name is too generic. It is actually part of the Kubernetes project itself. Or you could use the Amazon specific. It's actually an open source project from Amazon managing the node lifecycle, which is called Carpenter. So if you're using cluster autoscaler, the one from the Kubernetes group, and if you're using it on Amazon, you have a choice to actually configure them using node groups. That is how the cluster autoscaler works. Cluster autoscaler, in fact, can work with different cluster providers more than Amazon. And in this case, when you are configuring node groups, you can define the type of VMs, EC2 instances, that actually suit your cluster. And when you're using Carpenter, if you're on AWS, you might be able to actually utilize some of the feature from Carpenter because it is fine-tuned for AWS themselves. And when you're using Carpenter, you probably don't have to deal with node groups. But of course, you have the configurations, you have the flexibility to define the different type of node types that you want to actually supplement your cluster, and you can specify the architecture. All those configurations are available, but you might be able to get benefit of the AWS tuning so that your nodes are provisioned in a much faster. Now, the most important thing on fine-tuning your Kubernetes cluster is actually figuring out how to use those knobs. So we talked about measuring, understanding your application behavior, figuring out the thresholds, the inflection points, and adjusting the pods and nodes accordingly. Now, the main thing is, what is the right metric? What is the actual critical application behavior that you should be monitoring? So if you have seen the examples for autoscaling, you probably saw a lot of examples with CPU and memory. That makes sense because in Kubernetes, the resource allocation is defined using CPU, memory, and GPU. So utilizing CPU and memory to identify the application behavior makes sense. But is it always the right metric? Probably no. You could have a web application, for example, which is critical. The performance is critical. In those cases, your average latency might be a better measure for the application. So that might be the most critical attribute which actually indicates your application performance. So when you're using a metric to define your scaling, you have to make sure that you identify the application needs and the best attribute which represents the nature of your application. And now, let's say we define or figured out the metric that needs to be used for scaling. What is the right threshold? Is there like a standard threshold which works across the board? Even if you're using CPU and memory for your scaling needs, and if you have even a typical web application, is there a standard threshold? Actually, no. Each application is different. There could be applications which uses 1 GB of memory. There could be other applications which really needs like 3 GB to run properly. So absolute numbers are actually out of the box. So even if you're using CPU and you can go with a percentage usage, it probably may not be the most appropriate one. Each individual application could still behave in a different way. And it also could depend on the way you are configuring. Since you're actually trying to configure your application horizontally and vertically, you may not have a standard number which can be used across. So when you're looking at optimization in Kubernetes, you're actually trying to make sure that there is no wastage at all, zero wastage. So you really want to actually utilize 100% of your allocation. That may not be practical, but depending on your configuration, there could be applications which might work perfectly fine with 95% of usage. And some application may not work very well if you're saying 60% of usage. So it is very critical that the right threshold is figured out for the right metric. And when it comes to node and pod provisioning, there could be heterogeneous applications running in the cluster, most likely. And each application could have different needs. Some could be memory intensive, some could be relying more on the network, some applications could be dealing a lot of file IOs. So it is very critical to identify your application need and supplement the right type of infrastructure which can benefit the application the best. And now, even if you figure out all these things, is it just a one-time thing, done and dusted? Again, usually no. We are talking about more and more managed services so that users can build the application logic quickly. So we are actually dealing with a lot of faster release cycles nowadays. On an average, if you're dealing with microservices, you're probably dealing with bi-weekly release, or even faster than that. So your application requirements, your feature changes, along with it, your application nature also changes. So that means this whole process needs to be done on a repeated basis, on a continuous basis, so you don't miss out on any of the optimization opportunities. So if you put it all together, it is almost like a mathematical optimization problem. So you have a bunch of constraints, you have a bunch of variables to deal with, and the goal here is actually to tune those variables so that your constraints are met. So in this case, the constraints would be the cost, the performance, and if you have very strict SLAs, those ones too. And the variables are the one that we already discussed about the knobs. If you're scaling, you have to deal with HPA and VPA, and to configure them, you have to look at the right metric, which actually represents application behavior. Then we have to figure out the thresholds, which is almost always a moving target. And then we already talked about the application versions. Another critical thing is traffic. Most of the times when you're dealing with production, you're dealing with different type of workloads or different type of traffics into your applications. The traffic could change across the days of the week, across the hours of the day. So your application doesn't have like a standard configuration with which it can just handle all the different workloads. So it is very critical to analyze the application under different workloads and configure it in the right way. And now, when it comes to cluster, again, the infrastructure also plays a huge role in optimization. Of course, you have to choose the nodes, the right infrastructure, which suits your workload applications. And if you're using AWS, you have a lot of cost-saving options as well from AWS. So they offer you cost savings plans, EC2 savings plans, and also gives you the option of spot and on-demand instances. To really benefit from those cost savings, you have to identify how your application behaves and which applications, for example, can be used on a spot instance. So just to put it graphically, you're seeing the graph here, which is actually representing the behavior, the performance of a web application. So there are two lines here. The blue line actually shows the application performance, average latency of that application across different replicas. And the red line actually shows the corresponding cost, the infrastructure cost. And you have two shaded areas too. There is a green shaded area showing the performance requirements, and the yellow shaded area is showing the cost budget here. So as you can see, if you follow the blue line, you see that the application performance improves when you throw in more replicas, which is kind of expected. But after a certain number of replicas, even if you increase the replicas, your performance gain isn't that much. But if you see the cost, it is almost a linear line. It just increases if you have more parts allocated. So your problem at hand is actually to find that sweet spot where you are able to actually hit the performance requirement that you need while maintaining your cost budget. So in this case, it's that circled area which actually represents that sweet spot. Now this chart actually doesn't cover all the scenarios that needs to be dealt with. It doesn't cover the different application version, different traffics and all. So on the left, you can see two HPA configuration for the same application, but different versions. If you see here, it's using the same CPU metric for scaling, but the thresholds are totally different. That is because the nature of the application changed between the versions. To put it all together, if you look at the scope of all the configuration options that you have, let's take an example of an arbitrary Kubernetes cluster with around 100 microservices and an average bi-weekly release. So the variable combinations that you're going to deal with, of course, you have 100 resources to deal with. You have HPA and VPA to be figured out. You have to figure out which metric represents your application behavior the most. In this case, I'm actually going with a more conservative approach of 3 metrics. resource usage, and performance. And assuming that there are three different traffic patterns to deal with, 5 different infrastructure options. Again, I'm being conservative here. If you're using AWS, you have a plethora of choices for your VMs. And with 2 releases on a monthly basis, you're dealing with 18,000 different combinations to make sure your cluster is running at the most optimal way. So if you're trying to optimize, you need some way to actually handle this one. So we believe that this is going to be super hard for a human to do it. It just introduces toil. And if this optimization is going to be done by a human, there are more chances of errors. So you're probably not going to utilize all the cost optimization benefits, both cost and performance benefits. So in our company, we believe that these are kind of the lower order tasks which are better suited for machines by an autonomous system. So we have listed a bunch of the attributes we believe are the foundation of an autonomous system. So we believe that an autonomous system should be able to automatically identify your application topology. So in the Kubernetes case, it should be by either talking to the Kubernetes control plane or by looking at the metrics, identifying the topology. It should be able to communicate with your monitoring provider, understand your application behavior, correlate those metrics to the application and understand how your application changes over time, identify opportunities for optimization, safely reconfigure them. That is super critical. And the next thing is also super critical for autonomous system. It should be able to look at the changes that it made and figure out whether those changes has been effective or not. If it was effective, we can probably utilize those learning and put it back to the further changes it is making. If it did not work out, it should be able to abort, reset, or even call for help if required. This whole thing needs to be done on a per application and a per release basis. I hope I've given you high-level aspects that needs to be considered for optimizing Kubernetes cluster and the workloads in it. If you have any questions, please feel free to ask us. And we also have a booth here. So if you want to actually get more details on the autonomous system, please visit us. I'm assuming you're asking about the autonomous solution that we have, right? Either way, you have to actually rely on some kind of a metric which represent your application behavior. So if you're looking at the standard metrics, if you're looking at CAdvisor or KubeState metrics, it doesn't have the performance metric. So this is something that has to be added on top of it. You have to include that either if you're using some kind of an Ingress, Nginx, Envoy, all those things, or if you're using some APMs, they all actually deliver some kind of a latency metric representing your application. So that is required. That is critical if you're trying to actually optimize, because resource usage is kind of a good attribute representing how your application is behaving, but most likely you're looking at a performance metric. If you want to use CPU or memory as a performance metric, that is also possible, but usually that is not the right choice. You have to look at the metric which represents your application behavior the most. So it could totally differ. For web application, traffic count, requests per second, and an average latency might be the best one. But maybe there are batch applications which could be the number of jobs done or the number of messages that it handles. Those also could be good metrics, but that doesn't come out of the box from the Kubernetes. If you're looking at the CAdvisor, it doesn't come out of the box. So that needs to be added on. Are there other questions? Okay. Thank you, everyone.